Imagine 5 runners lined up at the same starting line. They all look identical right now, standing shoulder to shoulder, waiting for the gun. But each one obeys a completely different rule about how much slower they get as the track gets longer. The length of the track is a number we'll call n, the size of the problem you hand to an algorithm. It might be the number of names in a list, the number of pixels in an image, or the number of users in a database. As n grows, we want to know how much extra work each runner has to do. This is the whole idea behind big O notation. It isn't about how fast your computer is, or what language you wrote in. It's about the shape of the growth, how the work scales as the input gets bigger and bigger. Let's meet the runners by name. We have constant time, order 1, logarithmic time, order log n, linear time, order n, linear arithmetic time, order n log n, and quadratic time, order n squared. Keep those 5 in mind because we're about to watch them fall apart. Here's how we'll race them. We start n small, and we watch how far along the track each runner has to travel, which represents how many operations they perform. When n is tiny, they barely separate at all. Now watch what happens as I slide n upward. The runners start to fan out. The pack that looked identical a moment ago splits into a dramatic spread, some sprinting off the top of the screen while others barely inch forward. That separation is the entire story of this video. But a curve on a graph is abstract. To really feel it, we need to meet each runner up close and see the actual algorithm that runs at its pace. First up, constant time, order 1. This is the runner who never has to move at all. No matter how long the track gets, the amount of work stays exactly the same. Doubling the input changes nothing. A perfect example is grabbing one item from an array by its index. If I ask for the element at position 5, the computer jumps straight there in a single step. It doesn't matter whether the array holds 10 items or 10 million. Let's stress test it. Here's the array with 8 elements, and the counter reads 1 operation. Now I double it to 16 elements. The counter still reads 1, double again to 32, and it's still 1. That's the dream. Constant time is the flat line on our graph, the runner who stands still and always wins as n grows. Hold on to that image because almost nothing else behaves this well. Second runner, logarithmic time, order log n. This one moves, but astonishingly slowly. Every time you double the input, it only takes 1 extra step. The runner who barely notices the track getting longer. The classic example is binary search. Suppose you're looking for a name in a sorted phone book. Instead of reading every page, you open to the middle and ask, "Is my name before or after this?" Then you throw away half the book. You repeat that on the half that remains. Middle, compare, throw away half. Middle, compare, throw away half. Each guess cuts the problem in 2, so you close in on the answer with breathtaking speed. Here's the magic. A list of 1,000 items takes only about 10 guesses. 1,000,000 items takes about 20. 1,000,000,000 items takes only about 30. The input grew 1,000,000 times larger, and the work merely tripled. That's why we say logarithmic algorithms barely move. On the graph, the log n curve rises steeply at first, then flattens into a nearly horizontal crawl. Doubling the input is almost free. Third runner, linear time, order n. This is the honest, steady worker. If the input doubles, the work doubles. If the input triples, the work triples. A straight, predictable line. The everyday example is finding the largest number in an unsorted list. You have no shortcuts. You must look at every single element once, keeping track of the biggest one you've seen so far. Let's count. 8 elements means 8 looks, 8 operations. Double it to 16, and now it's 16 operations. Double again to 32, and it's 32. The work marches in lockstep with the input. Linear time feels intuitive because it matches our common sense. Twice the work for twice the stuff. On the graph, it's a clean, straight diagonal, steeper than log n but perfectly reasonable. Fourth runner, linear arithmetic time, order n log n. This one is a blend. It's the price of the fastest general-purpose sorting. A little worse than linear, but far, far better than what's coming next. The star example is merge sort. To sort a list, you split it in half, sort each half, and then merge the two sorted halves back together. That splitting gives us the log n factor, one level of splitting for each doubling. But at every level of that splitting, you still have to touch all n elements to merge them. So you pay n work across roughly log n levels. Multiply them together and you get n times log n. In practice, this stays wonderfully manageable. Sorting 1,000,000 items with merge sort takes about 20 million operations, not the trillion it would take a slower method. This is why n log n is the gold standard for sorting. If this made it click, subscribe for more visual math.